and that's actually a good example of new player friendly because you can't control the skeletons anyway. You can race fire blast someone, but that's it.
All right.
What confused me about that is at level 20 you can have his always raise fire blast everyone. So what happens if he has skeletons out and he raise fire blasts 5 people? What's going on here?
All right, so let me get started here. So the first thing I'm going to do is to talk about the homework assignment and give you the solution to the current homework assignment. And then what we'll do is we're going to start on the next homework assignment. It's not on Canvas yet, so we'll basically be looking at the new homework assignment as I talk about it.
You think some restriction you blinked before, you would face that
So,
direction before blinking?
First thing first, your current homework
It's
assignment.
easier now because you have more time to see.
Are there any specific questions about the current homework assignment, the one that's due this morning? Was it difficult? Was it easy? Was it
easier? Well, because we understood from the last one.
okay? All right. So this is your homework assignment that was due this morning. So we know that there are 3 calls to sub, right? Because you can see sub 3 times, 1, 2, and 3. But the order of calling those subs, now you can call those in varying orders, but you pretty much have to follow this order, right? You have to call this one first because the result of subtracting 4 from 6 is used in the second subtraction, where you subtract the result of the first sub from 17. That result in return is subtracted from 16. So you kind of have to do it in that particular order. And this is not recursive either. Recursion means the subroutine calls itself. Since you're not allowed to change your sub, which was not recursive, so it is not a case of recursion. It is simply a case of nested invocation, where the result of one invocation is utilized in another invocation. Okay. So we'll go ahead and work on this. At least I'll give you my solution. If you already have a solution, which I'm not doubting at all, you can just kind of compare the solutions. So in this case, we have LDI D0, okay, to initialize the stack pointer, which is not needed because when we reset the processor, all registers go back to 0. So this is actually not needed. But I put it here just to emphasize that this is what we do to initialize the stack pointer. When we are in main, the first thing we do is we have to push 4 and 6 on stack. So we have a LDI A4, decrement D to reserve a space on stack, and then STDA to push A, to push 4. And then we do the same thing with 6. And STD A. So that would push 6 on stack. And then we just need to save the return address. So this is main return address 1 because we're going to have 3 of these. So this is the first one. Decrement D, and then push it on the stack. Then we can do an unconditional branch to the subroutine, which is sub. And this is where the label main return address 1 should be located so that we can continue execution here. So technically speaking, the first thing you need to do is to deallocate the 2 parameters that are still on the stack. So the convention is the subroutine will get rid of the return address on the stack, but you will still have these 2 additional items on stack. One being the parameter of 6, the other one being the parameter of 4. So is that part okay? All right. The result of the first subtraction, which is 6 minus 4, which is 2, is now in register A. And it is serving as the second parameter to the second call of sub. So it doesn't do me any good when it is in register A. So one thing we need to do is to push it on stack. Do you guys have any questions I can answer?
Sorry.
All right. So now we decrement D, and then we do STDA. So this time we are not loading anything into A because A has the result of the previous sub. Yep.
Can't you just increment D once then instead of
Yes, you can. Yeah. Okay. So that was a good suggestion. So the suggestion was, since these 2 instructions they cancel out each other, can we just have one single increment? And the answer is yes. Okay. But I write it this way because the purpose of the second increment and the decrement, they belong to functionally speaking, they are different. They belong to different groups of operations. So even though you can do the optimization and say, hey, they're just undoing each other and get them out, it is still important to kind of point out that the fact that we only have one increment left is because these two cancel out. So let me just kind of re-emphasize that part. This is for deallocating the parameters. This one here is for pushing the result of the first subtract. It just turns out that these two instructions, when they're right next to each other, will cancel out each other's effect, and as a result, they can be both removed, so that we can have one single increment left. Okay, so the answer is yes. You can, in fact, get rid of these two, but I'm just going to comment it out because they are important to understand that we actually have these two instructions underlying. It just turns out that they can be canceled. Okay. So once we push the result of the first subtract on stack, we can now push 17 on stack. So I'm just going to be a little bit lazy here by copying and pasting. But every time I copy and paste, I have to be really careful, of what I need to change, because this time the labels will also have to be changed in order to have a second point of return. When this is returned, it is exactly the same thing, because the result of the second subtract is used as the second parameter of the, what I would call the first subtract, or the outermost subtract. So as a result, we're going to have the same thing here. We have increment D to get rid of the parameters of the second subtract, but then we also have to push A again on the stack. So once again, we have the same scenario as last time. These two instructions cancel each other, so they are not needed. But when you get rid of them, you have to get rid of both of them at the same time. Okay, so now we are done with that. It's just a matter of setting up the return point, which is return address 3 now. So main return address 3 is defined here. We just need to push that on stack at this point. Huh? Oh, right. Okay, thank you. And then JMPI the sub. So when everything is done, technically speaking, you can put a halt instruction here, but in order to help the stack stay balanced, it is probably a good idea to do 2 increments of D so that the stack remains, at the same place when you halt the instruction as when you started off the entire program. I'm not going to take any points off if you forget these 2 increments, but it is kind of important to remember that after each subroutine call so that you don't forget to do it when it does count. There's only one place that it doesn't count, which is the very last call in main. Everywhere else, if you do not deallocate the parameters, then you can end up with problems. So we're doing okay so far with this particular homework assignment. Yeah?
Left out putting the 16 on the stack.
Oh, I forgot to push 16 on stack, so we need to put it here. Okay. All right. So if I don't put that 16 on stack, the question is, what do you think this program is going to do?
A is going to be 0.
Huh?
A is going to be 0.
Why would it be 0?
Those subtracts.
Okay, so let's go ahead and analyze this program, because I like programs that do not work. Programs that work are boring, because you know what it's going to do, and go like, okay, we don't have to think too much about it. But when a program like this is missing something, okay, but thank you for pointing it out, okay, because now we have a better exercise, to do, okay, because otherwise it's just me yakking along, and you guys don't have to think about anything. So let's think about this, okay? So how do you debug this program? In other words, what do you think is going to be the behavior of this program, knowing that we missed one push?
It's gonna subtract something like earlier than I was supposed to. So it's gonna in this case, I think it's gonna subtract 50. It's gonna subtract main return address 3 from 15.
No. It's gonna
Subtract the address of main right out of 3.
Nope. Nope.
It's gonna for one of its parameters, it's gonna be whatever is above in the stack already.
But what is exactly about it? So we have to think about what the stack looks like at this point, okay? So the question is, what does the stack look like at this point? So starting from the beginning, okay? we got a decrement, we got a decrement, we got a decrement, we got one implicit increment is in the subroutine itself, and then we got one increment here, right? So, so it has one item left on the stack. Okay, at this point, so we push again, and then we pop, right? And then we increment again. In other words, the stack stays pretty much balanced throughout this execution. So we have only been using the last 3 locations on the stack the whole time. Does that make any sense? Okay. So if that is the case, the bug is right here. In other words, when the second call to sub returned, we push the result of that on stack. So what do you think this one is going to be located on stack?
It's FF.
It's location 255. FF, very good. Okay. So that means the return address, which is pushed after that, is going to be right below it, with at location 254. And that's exactly where the stack point is going to be, is at location 254. Is that making any sense? Okay, maybe it's better to kind of have use the document camera since I set it up already. Might as well use it. So that's VLC. And okay, kind of have to readjust this every single time. It would be kind of nice if the camera has some kind of a laser to put out the pattern of what it's capturing, so that way it's easier to align things. As it stands, it's not. It takes a little bit of visual. And then this thing is not fully aligned either, so it takes a little bit of to do it. There we go. Okay. So at this point, what is on the stack? Okay, let me see if I can superimpose. Yep, this works. All right. So at the label main return address, let's see what is on the stack at the label main return address 2. Okay. So we know at location 255. Okay, let me use a different color. My black. There we go. There we go. So at location 255, we have the second parameter to the second call of sub, which is, okay, I need to read my own code here. That's supposed to be 2. Okay, so we got 2. Okay, wait, switch back to this and back to mousepad. There we go. So we got location 255 has a content of 2. Location 254 has the content of, that's exactly what it is, right?
No, it's not. It's not 2.
No, that's just 2, which is the result already. So this is based on the store instruction that is currently highlighted in mousepad. So the next instruction or the next location is going to have the label of main return address 3. Okay. And the stack pointer is pointing here when we are going to do an unconditional brand to sub. Is that okay? So when we get to sub, okay, we are missing one thing, right? What we are missing, I'm going to use red here. What we are missing is the, what is it, 16? Yeah. So what we're missing is a 16 that really should be between the 2 and the return address 3. But it's not there, okay? So when you get into the subroutine is going to make assumptions. The subroutine, yeah.
Isn't that supposed to be a 17?
Is it 17?
Yeah, it's 2 solid stack.
No, 17 is already here.
You're subtracting 2 from 17.
Oh, yeah. 15 and it is 15.
15.
Oh, okay, yeah. So
Then you get 15.
thank you. So whatever the result is I think it's 15.
Yeah, 15.
Yeah, because 17 minus 2. Okay, so we'll make this 15. Sorry about that. Okay, that's 15. Okay, I need to invest. I need to go to Dollar Tree and pick up some whiteouts now.
Erasable pens.
That would be kind of cool too, but they don't come in like multicolored. They do?
Yeah, I just saw them the other day at my physics class, so I pulled it out. Whoa, they have a multicolor.
Multicolor with a pencil and it's erasable.
Pen.
Pen. Okay. Yeah, this one has a pencil too, which I like. Because you can use
Oh,
you can use it in zero gravity.
You can't have the cake and eat it too.
Huh?
You can't have the cake
Ah, correct. In which case, I'll just use whiteout. That's the cream, right, on the cake. But pencils are great because just in case, for whatever reason, I have to go to a zero gravity environment, the pencil always works.
It also works underwater.
Yes.
Assuming you're writing on a medium that works underwater.
Yeah, I think that was the joke of astronauts, with writing instruments in outer space. So in the United States, NASA developed this, really fancy pressurized, ballpoint pen refill thing, and then in Russia they just go like pencils. But sir, we forgot to bring the pencil sharpener. You got your pocket knife? Yes. Okay. I thought that was really interesting. Okay, so anyway, getting back to this one, we got 15 on at location 255. We got the main return address 3 in location 254, and the stack point is pointing here. But you have to remember the subroutine doesn't know about the mistake of the caller. So the subroutine is going to say, okay, this is what I'm expecting. I'm expecting this to be my return address. I'm expecting this to be my first parameter, which I'll call, is it XY? Doesn't matter. P1 is the first parameter. And whatever is on top of this is going to be my second parameter. Then you go like, but there are no locations on top of 255. I beg to differ.
0.
Location 0.
Which is the first instruction of the
Which is the
program.
first instruction, exactly. So when you look at the first instruction of the entire program, it is LDI D0. Okay, so the LDI D part is the first byte. Okay, so what does that come up to be? Well, we can find out exactly what it comes out to be. If I don't even need to do the assembler because I can just look at the description of the opcode table. That would tell me exactly what it would look like. The assembler sheet will do okay, but I can do it without that too. So I'm going to go to the wrong drive, wrong part of the drive. 310, 17 fall. Nope, shared. Okay, got the wrong place. Processor, and then what we want to look is at the opcode table. So when you look up the opcode table, let me magnify a little bit first. Okay, that should be good. There we go. So when you look up LDI, the instruction LDI, it's on row 24, and this tells you what the pattern should look like. So it is 0, 1, 1, 0. Those bits are going to be exactly the way they are, and then the 1, 1, which has to be there. And then the X6 is saying, okay, which register am I modifying? D is 1, 1, okay, because it's the last register of the 4. So it's 1, 1. So we have 6F here. So 6F becomes our second parameter. Okay, so switching back to the document camera, so we got 6F being our second parameter. 6F, so this is location 0. And location 0 has a value of 6F. And 6F is 6 times 16, which is 96 plus 15. So that would be 120. 6 plus 5 is 121, I think. No, that doesn't look right to me. It's also the same thing as 7 times 16 minus 1. 7 times 16 is 2. 122? So 122 minus 1 is 121, so I got it right. Okay, it just didn't look like the right number. Okay, so this time what the subtract is going to do is it's going to subtract 121 from 15. Okay, let's find out. So we have 0, 0, 0, 0, 1, 1, 1, 1. That is 15 in binary, and then we have 121 in binary. It is going to be.
We can see it. It's behind. We can see it.
Huh?
It's behind the mouse pad is blocked.
Oh, okay. Sorry. Just click it. Click. There we go. So this is our 15, And then the other one, we have the hexadecimal representation already, which is 6F. So that's going to be 0, 1, 1, 0, which is the 6. And then the F is 1, 1, 1, 1. Oh, that's easy. Because, you know, this part is all zeros. This part is 0. We have a 1 here. We have a 0 here. And then we have 1 here. And then we have a borrow, which we don't really care. Okay. But anyway, this is the difference. So let me just double check. 0 minus 0 is a 0. 0 minus 1 is a 1 with a borrow. 0 minus 1 has a borrow. And the 1 minus 1, which is the borrow from the digit before, is a 0. So I think that is correct. Okay. So we can now expect the result of this subtraction to be 1, 0, 1, 0, 0, 0, 0, 0, which in hexadecimal turns out to be a A0, because 1, 0, 1, 0 is 10, which is also known as A in hexadecimal. Is that okay? So let's find out. Okay, so what we'll do is we're going to plug in the wrong program, okay, the program that actually has a bug, into the spreadsheet and find out, you know, and then we'll run it in the simulator just to make sure that it is wrong the way that we predicted. Okay? Which is the most important part. The problem is not, the bigger problem is when something is wrong and we cannot figure out why or how it is wrong. Okay? This is a great exercise, by the way, and a great idea for exam questions too. Okay, so I'm going to copy and paste this into the source here. Okay, so we'll just put it here. And then from the previous class, oh, okay, I got it erased already from the previous class. So we'll paste the actual subtract subroutine from the assignment itself. So from the assignment itself, we'll download this. And then we'll open it from Notepad or Mousepad. So open in the temp folder. And we just need the subroutine itself. So another copy and paste. Paste over here. Okay. And we want to make sure that we don't have any errors. Okay, so all the errors there are no errors here, we're good. So we go to RAM file, we download this, download as CSV, and I'll call this one, you know, sub with bug. Okay, save, and then we have to go to a command line to start our Logisim. Oh, that's a better way to do it. In Linux and most Unix systems, you can type history, and it will show you, you know, the last, in this case, 2,000, you know, ish commands. So the one that I want to retrieve is 1999 because that's exactly what I want, and it complains. Oh, because of the lack of the tilde symbol. Okay, fine. Because I executed that when I was in the home folder, so I didn't need to specify the home destination. Alright, so we got the simulator. Control R to reset everything. And then we load the RAM image from the temp folder because we want to test the one with a bug. So it's sub with bug.csv over here. And we are expecting the program to terminate at the halt instruction just fine, but it will get the wrong value. And also the stack pointer will not be correct anymore because we actually have 2 increments. So now it's incremented to 0, 1. So we're expecting the register D or the stack pointer to be 0, 1, which is instead of 0, 0. We are also expecting register A to contain the wrong value, which is A0 instead of 1. Okay? So now we can run the program and see whether it does have those problems. Okay, Control K, and then, you know, it ran the program already. So we can only tell whether the program is correct or not by, you know, looking at this part here. So register A, which is the result of the last sub, did in fact have a result of A0 as expected, and register D is also 0, 1. So they are both incorrect because I forgot to push one of the parameters. But the most important part is, even when the program is incorrect, we were able to predict what it is supposed to do, which I think is even more important. So do we have any questions about this program, especially the buggy version? Questions? Okay. Now, where's Kevin? Oh, Kevin's right there. So, in the debugging bee in the future, hey, this is one of those things.
Maybe, yeah, we might turn assembly language on, why not?
Well, assembly language, I'm just half kidding, when I said that. But this is one of those, kind of tricky things, where it looks right, it's missing something, but the program is still running, it doesn't crash. It just grabbed the wrong stuff as the first and the second parameter. Okay, so the correct solution to the homework assignment is to put that 16 back, or whatever the value is, cannot remember. Yeah, 16. So we have to push 16 in the code. So to fix that problem, oh, this is the wrong one. This is the right one. So to fix this problem, we have to put that push 16 over here. So to fix the problem, we just have to do a LDI A16, and then decrement D, and then do std A. So that will fix the program and have it return a value of 1, and also have the stack pointer to return back to 0 when we get to the halt instruction. So are we doing okay so far with this program, with the solution? Okay. How many people did not get this right the first time? Okay. And how did you debug your program? They are
Through the
tracing?
yeah.
Okay, so that was helpful because you were able to tell, hey, it's not supposed to go here, or this value should not be in the particular register. Okay, that's good. Does anyone do anything differently in terms of debugging the program? You can always just analytically read through the program and just kind of say, okay, did I miss something here? Did I mistype something here? But that's actually harder compared to using the trace to help you find out, okay, this is exactly what happened, but why is it doing this instead of that, what I was expecting. Very good. All right, so for your next homework assignment, I'm going to give you I'm going to reverse the role. In other words, in this homework assignment, you're doing the calling. Okay, I give you the subroutine, you're doing the calling. So in the new homework assignment, I'm going to do the opposite, where I will be doing the calling, and you are going to implement the subroutine. Okay, so the subroutine is going to be like this: uint8 underscore t. This is it has no. You cannot use this type in assembly language programming. All this is really saying is the type is an unsigned 8-bit integer. That's all it's saying. Okay. So the subroutine is going to look like this. Remember divide? It's back. So in this case, we're going to do it like this. The first one is a pointer pointing to the remainder. The second parameter is your dividend. This is all going to be in the in Canvas, so you don't have to actually copy this. And the last one is our divisor. There we go. So we have all the information needed in order to perform a division. So if I were to document what this subroutine is supposed to do, so this will perform a division of dividend divided by divisor. Okay, that's what we need to do, which is not surprising because of the name of the parameters. The return value is the quotient of the division if P remainder is not null, then store the remainder to where P remainder points to, else do nothing with the remainder. That's it. Okay. So I will even give you the pseudocode, for the actual division part, and also what to do with the null pointer and stuff like that. So we already know how to do this. Okay, we need one extra variable here as our as our quotient. Okay. So we have our quotient here, and basically what we do is we make sure quotient is initialized to 0 first, and then we can use the successive subtraction method, where we say as long as dividend is greater than or equal to divisor, stay in the loop. In the loop, for each iteration, what we're going to do is to say dividend minus equal to divisor, and we also want to increment quotient. When this is all done, then we have to do something with p remainder. So we say if p remainder is not null, okay, null is basically 0, so you're comparing to 0. If it is non-null, then whatever it points to is going to store the remainder, which is actually in divisor, dividend at this point. So dividend is here, and this is going to return quotient. So that's basically the C code corresponding to what you need to do in assembly. The first part we have done already. You can actually reuse code if you want to get this part done. So what is left to do is the conditional statement, the return, and that's your homework assignment. So I'll be doing the calling. Okay, so I will set up the stack. I will transfer control to your subroutine, but when you return, I will check a few things. Okay, if I give you a non-null p remainder, I'm expecting the remainder to be stored somewhere. Okay, if I give you a null as a p remainder, then I'm expecting no location in memory to be changed. I'm expecting the quotient to be returned in register A in all cases. So are there any questions about this? Yep.
Is it supposed to be if dividend is not null?
If
Or is it?
it's p remainder.
So then what is p remainder then? Because
P remainder is a pointer to a 8-bit integer.
so it wants to give a remainder if you ask for a remainder, basically.
Exactly. So if I ask for it, which is signified by a non-null pointer, then store it. If not, just give me the quotient. The quotient. Yep, exactly. All right. So let me save this file. Okay, so save, and I'm gonna save it in my temp folder as divide subroutine. And this one has a .c extension because it is a C code. And since I'm saving it already, might as well test it to make sure it does compile, just in case I did something stupid. Ooh, I did. Well, that's because uint 8_t is defined in a header file, stdint.h. This is also something that you might want to start to use in your other classes too, because a lot of times, if you specify the width of the integers, your program become a lot more portable. So I think that's the only thing that's missing. All right, save again, just to be sure. Then we go back to the browser, and we'll make it a homework assignment. Making an assignment is easy. Grading it is not. At four-year universities, professors have what we call readers or graders to help them grade all the homework assignments. They also have TAs or teaching assistants, so that they don't have to talk about the solution of previous homework assignments or to talk about how to. They don't have to help you do the homework assignment. That's the job of a teaching assistant. Not here. Okay, so.
What if they don't know?
Huh?
What if they don't know?
The TAs?
Yeah.
Well, it depends. I mean, sometimes you get a TA who doesn't care, right? I mean, so So the whole class will not be able to get the assignment done. Other times you get a more responsible TA, and the TA will try to figure out how to get something done, and then the whole class benefits from it. I can tell you some experience, as I type this. Okay, so download this C program as a implement div sub in GTP assembly language. Okay, putting the cursor here because I'm going to insert a hyperlink to it. So we go to Files, Upload. Divsub.c. Open. I think there was one time I forgot to click Upload and it didn't happen. Okay. So your subroutine needs to. So I'm just outlining, what your code needs to do. Okay. Assume parameters are pushed on stack in reversed order. That means, okay, let me see, where's the indentation? There you go. So this means the last parameter is pushed first with the highest address on stack. Okay. Assume the return address is pushed last. Okay, which means when the caller gets to your subroutine, you can assume the stack pointer to be pointing to the return address. So everything is just consistent with what we talked about in class. I'm just spelling it out here. Assume all registers can be changed, but register D is the stack pointer. So don't mess around with the stack pointer. The return value is in register A. The subroutine deallocates the return address, and also the subroutine continues execution at the return address at the end of its execution. All right. So is that okay? I'm just really spelling out things that we have been talking about already in class, but I'm just putting it all in the homework assignment. So are we okay so far? Okay, excellent. Okay, so I'm going to put 30 points here. 30. Yep. I need my gaming keyboard. Submit it online. File submission. And the due date is next week. So it'll be the 9th at 9 a.m. Save. There we go. New assignment. So is that okay? All right. Okay, so for the next, about 35 minutes or so, let's talk about decompiling a program. If I give you some code that is in assembly code, how do you decompile? In other words, how do you figure out the original C code corresponding to it? That's the question. So what do you think?
If you do have the assembler looking at the codes, what they do. Okay.
We know the assembly code. So I'm going to give you the actual assembly code. So given the assembly code, how do we quote unquote decompile the program so that we can actually figure out the original C code that compiled into that assembly code?
Look for labels first.
We look for labels. Okay, very good. So so instead of just talking about it, I'm going to go to a folder with all the previous exams. I will make these all available to you guys too. So let me see. Let's go to Spring 17 because I'm pretty sure in Spring 17, at least in exam 2, I have a question like that. So I'll share this one too. So no need to worry or try to copy everything onto your paper. So let's see, what were the questions? I guess not. Okay. So the pace I move through the material is different this year. So that's in the final exam of the previous semester. Okay, 17 spring, final exam. And this is a copy of the one before. Well, let's check out this one first. There we go. So we have a decompiling example here. So let's check this out and figure out, what we can do with this. So instead of looking at it from here, I'm just going to copy and paste it into Notepad because it's a lot easier, with a larger font. So that's a new, and just paste it here. Okay. That's the assembly code with no comments whatsoever. Okay. So what are you going to do when you look at this code and I'm asking you, what is the original C code? What would the C code look like in this case? What do you think? What would be the things that you're looking for, like the anchor points, where you say, okay, we know for sure what this is, then we can either go forward or backward a little bit just to figure out, how it is set up, the more specifics about that. There are certain patterns that you can definitely see. We're putting some kind of label into a register, and then the label is defined later on, and then whatever register gets the label is pushed on the stack. That is telling you something about what? Like this code here. When you look at this code, what is that reminding you that, oh, okay, I can recognize what this is doing. Now, it might be doing something before that that is kind of important too, but we can definitely recognize what this is. What is that?
Function call.
It's a function call. Okay, very good. Okay, so we are saving the return address onto the stack, and then we continue execution in the subroutine. Okay, so we can kind of recognize this sort of thing. So as you recognize these things, you just say, okay, we can recognize this portion. Let me do it in a slightly different way. Okay, you cannot do this in an exam, but I can do this in class because it is a better way to explain things. So I'm going to use a new spreadsheet to do this. Okay, and I'll explain why I use a spreadsheet for this purpose. Okay, this is the original program, and we'll zoom in, just to make sure that the text is easier to see. Okay, the reason why I use a spreadsheet in this case is because I can now do something like this. I can say, okay, this chunk of code is corresponding to one thing. So now I can go to Format, go to Merge Cells, and now we can say, oh, this is really the same thing as calling sub1. That entire block of code from row 13 to row 17 is really just calling sub1. Are we doing okay so far? When you have a subroutine call, then the next question you have to ask is, does it need parameters? Okay, how do you know whether it needs parameters or not?
Look above it.
Right below.
Look above it and also below it, okay? Because there has to be some kind of consistency. If you look below, this one has got 2 increments below it, 2 increment Ds below it. And the usual thing that I do, at least this is what I do consistently, is I'm deallocating the parameters right after the subroutine call. If I'm incrementing the stack pointer twice, that means I'm using 2 bytes on stack as my parameter. Is that okay? So this prompts me to go look back and say, okay, what did I push on stack as parameters? Okay. So I'm going to combine these two. Okay, so go to Format, Merge. Let's see. Oh, it's not available. Why not? Okay, this time it is. Okay, merge all. This is for deallocating 2 bytes of parameters. Okay. Which means I'm expecting there are 2 bytes of parameters set up earlier. Okay, like here. All right. So what are the signifying parts that tells me that I'm pushing parameters on stack. A decrement of D followed by a store. Does that make any sense? So whatever is in between is what we are pushing. So in this case, we are decrementing B and we're pushing B on stack. Okay, so we'll look at these three and we'll say, okay, these three kind of work together. Okay, and we'll merge cells and say, you know, we don't know exactly what is pushing, but we know we're pushing, this is the first parameter. We know that, okay, but we have no idea what exactly we're pushing because we don't know what is in B. So that makes this the pushing of the second parameter. Okay, so we'll once again, you know, use this technique here and say push the second parameter. Are we doing okay so far with the analysis of the code? Okay, so now we look at this and go like, all right, so what is B? Well, it looks like B had a value of 4. We store it somewhere on the stack, okay? But by the time we get here, by the time we push this register B on stack, parameter 2 has a value of 3. By the time we get here, parameter 1 has a value of 2 because we keep decrementing B as we push the parameters. Is that okay? The next question now is, well, but does the subroutine return a value? We know we are calling the subroutine with 2 and 3 as parameters, but then the next question is, does it return a value? If it did return a value, it will be in register A, and I'll be using A for some purpose, right? Aha! I am using A. In fact, this code you should recognize from today's discussion. I'm using the result of the first call to sub as a parameter to some other call later on. So we know it is returning a value. We know sub1 returns a value. Okay, that is stored in register A. We don't know exactly what it is, but we can say, now we know this call can be summarized as, you know, some kind of value is sub1, 2, 3. We know 2 is pushed as the first parameter. We know 3 is pushed as the second parameter. So as I work on the code, I'm, you know, kind of annotating what I find and, you know, and adding to it. Okay. Okay. So let's move on to sub 1, okay? Because, you know, I know there's some other stuff that we have to deal with here, but we'll move on to sub 1 and try to figure out what it is going to do. So this is in sub 1. And, you know, we'll do the usual stuff, okay? So the usual stuff is to say this instruction, you know, makes B equal to D, and they are both basically the address of the return address. One thing you're guaranteed is register D is always pointing to the return address, which is also saying the same thing as register D is the address of the return address. Is that okay? So that's always a given. But since I'm copying this to register B, that is what it is. And now that I have incremented B, B becomes the address of the first parameter. And I'm dereferencing B while storing that into register A. So register A now has parameter 1. I'm incrementing B, which used to be the address of parameter 1, but 1 is right on top of parameter 1. Parameter 2, very good. So B is now the address of parameter 2, which I dereference and then put it into register B. So register B is now parameter 2. And you recognize this. We have register A being parameter 1 minus parameter 2, which is the same thing as your homework assignment, right? And then this is the return address. Because register D was never moved in all of these instructions. So register D is still pointing to the return address. So that means B at this point is the return address because register D is the address of the return address. So B is the return address, which we deallocate and continue at the return address. Okay. what is that reminding you of? Your homework assignment due today. But the other way to look at this is to say, oh, this is the same thing as saying return param1 minus param2. Is that okay? The other thing we can also say is this is a function that returns some kind of integer. Okay, we don't know whether it's signed or not, and it is expecting two parameters. One is one is an integer, 8-bit integer. The other one is also an 8-bit integer. Now you can say int 8, okay, because it's 8-bit wide, but this is fine. Okay, if you just tell me that it returns an integer, it takes on two parameters. Each one is an integer as well, and it returns the x minus y. Okay, to use the same terminology. If you say this returns x minus y, you get full credit for this section. Is that okay? All right, so now that we know what sub1 is doing, we can now finish the rest. Okay. So we are using sub1 as the second parameter. So I'm going to combine these two blocks here, these two cells, and say sub1, 2, 3 is a parameter. And then we call sub1 again, okay? So this part here, this entire thing is calling sub1. And you might say, hey, it seems like we have the same bug as what we talked about earlier today. But this one actually does not have that bug. Okay. So this is calling sub1. So you might say, okay, but what else is on the stack? There's actually some other stuff on the stack, isn't it? So we are decrementing D, and then we decrement D again, and then we store something to that location. So at this point, D is 255. At this point, D is 254, right? And what we are doing here is we are storing the address, the location at 254 now has a content of 4. Is that okay? Is that remaining to be there throughout everything else that we have talked about? We never deallocated that. Okay? We never deallocated that. So that means when we are calling sub the second time, we still have that 4 on the stack as our second parameter. Which also means when we say sub1, 2, 3 is a parameter, we can actually say it is parameter 1. Because now when we get back here, this is our second parameter. The second parameter has a value of 4. Is that okay? So when we combine all of this, okay, so this is just for deallocating the parameters. So merge all, deallocate parameters. Okay. So when you look at this entire thing, everything from here all the way back here. So I'm going to merge all of these cells. Merge cells. Okay. So all of these is really saying that we call sub1 twice. And we are using the first call to sub1, which has parameters 2 and 3, as the first parameter itself. And then 4 itself is the second parameter, which is set up here. Is that okay? And then what do we do with that A? We put it into register D. Register D is now 255. So that is a local variable. How do we know it's a local variable? It's allocated on the stack, and yet it is not used anywhere else. Okay, it's not used in a subroutine. It's not passed as a parameter. How do we know it's not passed as a parameter? Since it's on the stack, how can we differentiate something that's on the stack but not passed as a parameter? The question is the subroutine using it? Okay, let me show this on a piece of paper. I think that will help explain what we're doing here. Okay, and to do that, let's do it this way. I'm gonna slide this one on the side, go back to the document camera, and nope, that's not what I want. That, there we go. Okay, so when you look at how we use the stack, I need to realign the edges a little bit. There we go. Okay, so we basically, this is location 255, 254, 253, 252, 251. I don't think we need all this many. So register D originally points to 256, quote unquote 256, which is location 0. So after the decrement on row 3, it is now pointing here. It didn't do a single thing using that location, okay? Which is the first clue that this is going to be a local variable. Because if this were a parameter, we would have initialized a value into that location. Let me say that one more time, because this is how you can differentiate whether we are setting up a location on stack as a local variable or as a parameter. If this location was used as a parameter, I'm not going to skip it. I'm going to say, oh, we're going to push a specific value to this location. But when you look at the code, I'm just decrementing D again, right after the first decrement D, which means I'm not going to put any specific value here. I'm just saying reserve this byte, but not do anything with it. Okay? So when we skip that location and go to location 254, we can see that we push a value of 4 here. And then when we go further down, we push a value of 3 into location 253, and then we also push a value of 2 to location 252, and then we push the return address, which is main underscore ret1 at location 251. So is this part okay? I mean, can we see at least how the stack is set up at this point? Is that okay? The subroutine, which we identify as the subtracting the subroutine, is going to use 2, 3. Oops. It's going to use 2, 3 as its parameters, and by the time it returns, this is going to be gone on the stack. Okay, so we have this one gone on the stack after we return from sub 1. Okay, and then we have 2 increments after that. These 2 will be gone. Is that okay? So let me scroll down to that code here. So after these 2 increments, then we only have the 4 left on the stack. Is that making any sense? And then we push A back on the stack. In other words, we're pushing the result of sub 1, 2, 3 on the stack, which means this location, 253, now has a value of 1. It's -1 actually. Yep. Okay, so it has -1 on stack. Well, if it's signed, it's -1. If it is unsigned, it's 255. But either way, it's the bit pattern corresponding to 1, -1. Is that okay? Then we're going to call again, because then what we do is we push main return address 2 on stack. So main underscore return 2 is going to be pushed to location 252. Yep.
Can't see what you're writing.
Oh, okay. There we go. Thank you. And I think I forgot to focus the camera also. There we go. So is that okay? And we probably want to put it down a little bit so we can see more. There we go. When the second call return, which is here, we increment D twice. Now remember, this return address is deallocated by the subroutine itself, which means by the time we get to the second decrement on row 28, we are now removing these items on the stack. But register A is going to have -1 minus 4, which is -5. Okay? So by the time we get to this instruction here, to store something into register D, well, what register D is pointing to? Register D is now pointing back to location 255. So location 255 is actually what is storing the value of -5 in binary. And the last increment will also get rid of this because we are now at the end of main, and at the end of any subroutine, it has to deallocate its own local variable. So that makes this local variable go away by the time we get to line 30, right before the halt instruction. So is that okay so far? Yep.
Are you actually creating uninitialized local variable and then one that takes decrements to make the parameters?
Yes. In other words, when you look at the actual code of this program, okay, in C, we have main, and inside main we have its own local variable. We'll call it V. We're not going to do anything with it initially, but V equals to sub1, 2, 3, and the 4 here. That's main.
I thought you were doing something like into V and then X or something like that. That would equal to 4 and then push X.
Nope. No, the 4 is not really a parameter. It's not a local variable.
It's just a.
The reason why we know the 4 is not a local variable is because it is utilized by a subroutine. By the second call to sub1, that 4 is consumed, that it is utilized. So that's why we know it's not a local variable.
Because
Yep.
you could actually make it one more decrement and keep it there, like an initialized variable.
But then if you have one more decrement, then you have 2 local variables or 2 bytes as local variables.
Yeah.
Right.
But that's what I was thinking of the first time.
Oh, okay. Yeah, so basically the answer is this. The answer is main has a local variable that we call V in this case, and V equals to sub1 of sub1, 2, 3, and then a 4. That's the original C code. So we kind of do okay so far with the analysis of the assembly code in order to reverse it back to the original C code. That's okay? All right. Let's pick on something that we have seen also already. We got about 10 minutes left, so this would be a good exercise, but we can talk about the solution next time. It is something that we have seen already, and I have to recall this thing here. So this is the subroutine that we have, and then we have a CPRD CD. Do a increment C. See, I have to remember the code or work out the compiling in my head right now. We do LD A. I to L1, that's L1, they're the same. If not, okay. I'll upload this. You know, there's no way you guys can actually copy this. Not the way that I type, right? This is all done. Do LD. There we go. Okay. Unless you have a photographic memory of stuff that we have done in the past, you probably cannot recognize this code. So I'm just gonna put this one here and let you guys disassemble it. Okay. So I'm gonna save the file. Okay, this is going to be saved as temp folder. We'll call it mystery.ttpasm, and I'll upload it to the website. So this way, you know, you guys can download it and try your best to disassemble this program. So we'll put it into the module. So this one is not going to be graded, you know, it's just something that I want you guys to work on over the weekend, so that on Monday, we'll take a look at this. On Monday we'll, there we go, okay. So we'll add file. There's no upload button, but I think it does it automatically. There we go. All right. So this mystery.ttpasm is what I kind of want you guys to spend some time to look into and see if you can disassemble this program. I think it is corresponding to one of the subroutines that we have done already in this class, and I'm just mentally going through the code myself to make sure that it is actually correct. Oh, I forgot what. I think L1 is defined. Okay, L1 is defined. Okay, that's good. Okay, so we got L1. Otherwise, we got the LDB with C, increment B, decrement D, put it there, decrement C, copy that to B, increment B, decrement D, put it. Copy that onto where D is pointing to, load it with return address 1, decrement D, push that on the stack, jump to subroutine, decrement. Yep, I think that's, oh, okay, forgot one thing, JMPI to L2, because this one needs to go here. Nope, I got it wrong. Sorry. Okay, I'll okay. Yep, I forgot. Okay, sorry about this. So if they are the same, we're going to want to go to JMP, go to L1. At L1, okay, JCI. Otherwise, we do an unconditional branch to L2. And at label L2, that's what we do. We might still need an L3 here. This is L3. Okay. All right, so getting back to here. So at L1, we know they are the same. Okay, there's one more thing we need to do. LDI B0 and CMP AB again. JZI to L2. There we go. Okay, I think that's the correct code. Yeah, we'll still do it correctly. Yep. Okay, so I think this is the right code. Let me save the file one more time. Does anyone recognize this code? You don't have to tell me what it is, but I just want to see if anyone has already recognized this code.
Is it the string compare?
Yep, it is. Indeed, it is. Okay, so the question now is, how do you? Okay, did you recognize it because of the structure of the code, or did you recognize because you actually remember the sequence of the instructions?
Well, you hinted at something we did before, and the first instruction was a compare, and the most recent thing we did with compare was string compare.
And then the label 2 or 3 now was doing the sum.
Yeah, but it can be. That only means it's recursive, right? It doesn't say anything about whether it's a string compare. Okay, but I'm gonna put it here anyway. So I'll put it up, just because that's what I said I would do. Okay, and I want to double check to make sure this is the one. What? It doesn't know how to handle the extension. Okay, save file first. Okay. I just want to make sure this is the correct version and not the one that is incorrect. Okay. And it is the correct version. Nope, this is the wrong version. No, this is the right version. Okay, never mind. So it is the right version. So when you go to Canvas, you can download that. So instead of okay, so what you did is good. Okay, you recognize it is the string compare. So now the question is, instead of going back to the previous notes to look at the C code of that string compare, use the assembly code to reverse engineer the whole thing. To figure out, okay, what is being compared to what, and are we dereferencing? Are we just looking at the variable, the parameters, and so on and so forth? What are we returning in each case? So I want you guys to kind of analyze this program and actually come up with a C code, and we'll talk about it on next Tuesday. Is that okay? Yep. Go ahead. Huh? Our next exam is at least 1 week from next Tuesday, depending on whether we can get this done on next Tuesday. So it's always at least 1 week from the time when we talk about the practice exam, and I'm not counting today as talking about the practice exam. Okay. Alrighty. So we'll go to the lab for those of you who want to work on your program in the lab, or have any questions related to the class to ask during the lab time.